Good day, students. In this clip, we're going to be going over some problems reviewing the whole process of derivatives. So let's go ahead and take a look at question number 1. So for problem 1, we are to find f prime of x if f of x is equal to 2x squared plus 3x. We're to do this using the definition, the limit definition of derivatives, using the limit definition of derivatives. Okay. All right. So if we wanted to use the formulas, it would be easy for us to compute what this derivative is. So let's do down the side. So f prime of x using the power rule is going to be 4x plus 3. Okay, so when we use the limit definition of derivatives to find the derivative of this function, we should expect to get 4x plus 3 as our final answer. All right, so let's write down what the limit definition of derivatives is first, and then we'll go ahead and start looking for the derivative using the formula. Okay, so the formula, f prime of x, there are two of them, but this is one that I'd like you to use. Limit as h approaches 0 of f of x plus h minus f of x, and this divided by h. Okay? Alright, so let's go ahead and apply that to this problem. So f prime of x is going to be the limit as h approaches 0. Now, f of x plus h is what you get when you replace the x's in f of x with x plus h. So we're going to have 2 times x plus h quantity square plus 3 times x plus h. This is f of x plus h minus f of x is going to be parenthesis 2x squared plus 3x. Okay, do not forget the parentheses when you have the minus here. That's a common mistake most students make, so keep that in mind. And that over h. We can clearly see that plugging in, directly substituting h into this equation will be problematic because we'll be dividing with a 0 value which is undefined. So what we have to do is simplify this equation, this expression completely, and then we can plug in 0 for h. Okay, so let's go ahead and expand this term, x plus h squared. If you expand it, you're going to have 2 times x squared plus 2xh plus h squared, and then distribute 3 to this, you're going to have plus 3x plus 3h, and then here just distribute the negative, you have minus 2x squared minus 3x, the entire numerator divided by h. Okay, we're still taking the limit. Okay, so let's see what we can do here. We can distribute this 2 to all these terms here. So when we and also if you note the 3x and the 3x, this one's cancel out right there. And then let's go ahead and distribute the 2 to everything. So we're going to have the limit as h approaches 0 of 2x squared plus 4xh plus 2h squared plus 3h minus 2x squared, that entire numerator divided by h. Okay, now let's see what happens in the numerator. You notice that let's see, 2x squared minus 2x squared cancel out. So anytime you do this correctly, the terms you're left with after simplifying the numerator completely must have h as a common factor. Okay, if you can't factor out h from what you have left after simplifying the numerator completely, then you made a mistake somewhere. Okay, so you can clearly see that h is common in these 3 terms. So what we're going to do, that's going to enable us to factor out the h and cancel it with the denominator, all right? And then we can plug in 0 for h without any complications. So let's go ahead and factor out the h. Factor out the h, we'll have h factored out, 4x plus 2h plus 3. That divided by h. Okay, and then you have some cancellation action happening here. can divide the top and the denominator by h, and then you have the limit as h approaches 0 of 4x plus 2h plus 3. Now we can just plug in 0 for h, and that's going to leave us with 4x plus 3. All right, because this term attains a value of 0. And there goes your derivative, and we can see that it checks out with what we expected for f prime. Okay, so that's what f prime of x is, 4x plus 3. All right, let's move on to the next question. All right, so for problem 2, we are to find f prime of x if f of x is equal to the inverse sine of log base 3 of x to the third plus 2, that entire expression divided by cosecant of 4 raised to the x to the third power. All right, so we can see here that we're going to have to use the quotient rule. All right, so the numerator is u, and then the denominator is v. Okay, let's review the quotient rule real quick. U over v prime is equal to vu prime minus uv prime over v squared. Okay, so that's the first formula we're going to use. Then when we're looking for u prime and v prime, we're going to talk about other formulas. Okay, so what we're going to do is, since u and v are very complicated, we can differentiate them individually, and then we're going to just plug the respective values into this derivative function right here. All right. Okay, so let's go ahead and list them. So let's start with u. Extracting the numerator u. U is the inverse sine of log base 3 of x to the third plus 2. All right, we're going to be using the inverse trig function for sine, the derivative of that, then the derivative of logarithm base b, and then the power rule to differentiate this polynomial function in here. Okay, all right, so let's review the formulas that we're going to be using here. So the inverse sine of x prime is going to be is 1 over the square root of 1 minus x squared. Okay, and then the derivative of log base b of a, if you differentiate log base b of a, that's going to be 1 over a times the natural logarithm of b. All right. All right, so let me change the variable for this one here so you don't get confused as viewed as a constant. So let's say we're doing log base b of x. So it's going to be 1 over x times the natural logarithm of the base. Okay, and then we know what the power rule is. All right, so we're going to use these two formulas to find the derivative of this function. We're going to be using the chain rule here. Okay, so let's go ahead and take a look at, we're going to start u prime. We're going to start with inverse sine. So when we're doing inverse sine, log base 3 over x to the third plus 2 is going to be our u. Okay, so we're going to leave that fixed and then just differentiate the outside. So let's use this formula right here. We're going to have for u prime 1 divided by the square root of 1 minus u in this case is going to be that. So the square root that the square root of 1 minus this entire argument prime square, so 1 minus log base 3 of x to the third plus 2 square. Okay, so that's the derivative of the outer function. Now, using the chain rule, we're going to shift our attention to this log base 3 of this term right here. Okay, So using the chain rule, this will be our u. So if we take log base 3 of u, it's going to be 1 over whatever u is, which is x to the third plus 3. So x to the third plus 3, plus 2, multiplied by the natural logarithm of the base, which is 3. So ln 3. Okay? So that's the second function. Now we're going to go to the innermost function, which is x to the third plus 3. Using the power rule, that's simply going to be 3x squared. All right? So there goes u prime. So let's write it. Let's make it look pretty. So u prime is basically going to be 3x squared divided by, in the denominator we have ln 3 times x to the third plus 2 times the square root of 1 minus the log base 3 of x to the third plus 2 raised to the second power. All right, so that's u prime. All right, let's go ahead and look for v prime. So I'm going to split it down the center, see if I can fit it in here. So to look for v prime, we're going to have to first of all write down what v is. So let me move this to the right a little. All right, so let's write down what v is. V is the denominator, right? So v is equal to cosecant of 4 to the x to the third. All right, so there goes what v is. All right, so what's the derivative of, we're going to be using, to find v prime, we're going to be using the derivative of cosecant and also the derivative of a to the x formula. Okay, so let's list the formula we're going to use here before we find the derivative of v prime. So we know that, let's write it here, cosecant x prime is equal to negative cosecant x cotangent x. Okay, and then a to the x, if you have a constant raised to a functional exponent as indicated by a to the x prime, is going to be a to the x times the natural logarithm of a, of the base. All right, so there goes the formula for exponential functions. Okay, so let's go ahead and apply it here. So we're going to be using the chain rule. V prime is going to be, let's start with the outermost function, cosecant. We're going to hold this fixed, unchanged. So the derivative of cosecant is negative cosecant u cotangent u. So if this is u, it's going to be negative cosecant 4x to the, 4 raised to the x to the third times cotangent 4 raised to the x to the third. Okay? Alright, so we're done with the outermost function. Now let's shift our attention to the inner function. To differentiate that, that's going to be a to the x ln x. Basically, whatever you were differentiating, a to the x, you rewrite that 4 to the x to the third times the natural logarithm of the base times ln 4. And then we're going to multiply it by the derivative of the innermost function, which is x to the third, and that is going to be 3x squared using the power rule. All right, so that's 3x squared. Let's write that down, times 3x squared. All right, so let's go over what we just did again. So we differentiated cosecant first to get cosecant and cotangent, holding the inner fixed for x to the third, for x to the x to the third, and then we differentiated for x to the x to the third using the power rule here, exponential rule. So we had a to the x ln a, so this is a to the x, the original problem, times the natural logarithm of the base, which is 4, and then using the power rule for x to the third, we have 3x squared. Okay, so if we write it nicely, this v prime is going to be negative natural logarithm of 4 times, we don't have to put times it. Natural logarithm of 4, parentheses, times 3x squared times 4 to the x to the third, cosecant 4x to the third, 4 to the x to the third, cotangent 4 x to the third. All right. Okay, so let's put everything together to get our final answer. So we're going to be using the quotient rule. All right. So let's rewrite it here. U over v prime is basically v u prime minus u v prime over v squared. Okay, so let's go ahead and do it. We're going to have the final answer, f prime of x. We don't have to simplify too much, just write it as it is. So v is cosecant 4 to the x to the third times u prime, which is 3x squared. So we can put, let's put 3x squared here, doesn't really matter. 3x squared over this entire thing. So it's going to be over the natural logarithm of 3 times x to the third plus 2 times the square root of 1 minus log base 3 of x to the third plus 2 squared. Okay, so that's v u prime minus uv prime. So u is the inverse sine of log base 3 of x to the third plus 2. Okay, so that's v, and then that's u, and then v prime is this entire expression right here. So since we have a minus, it's gonna change this to a plus, and then we can just put this entire expression in there. So it's gonna be the natural logarithm of 4, ln 4 times 3x to the second power, 4 to the x to the third, cosecant 4 to the x to the third, cotangent 4 to the x to the third. Okay? Alright, so this is vu prime minus uv prime, and then that entire expression will divide by v squared. Okay, divide this by v squared. So v squared is simply cosecant square of 4 to the x to the third. Okay, so that's it. You don't have to simplify it any further. It's just this is good enough. So all right, so let's go ahead and consider the next question, problem number 3. All right, so for problem 3, let's use a new page. We have to find the derivative of f of x equals the square root of x to the third plus x divided by the inverse secant of x to the third. All right, so to make this easy to compute, we can rewrite this function as x to the third plus x over the inverse secant, or the arcsecant of x to the third, all this raised to the raised to the 1/2 power. All right. So the new formula we're going to be using here that I haven't gone over the formula is the inverse secant formula. So the derivative of inverse secant or arcsecant of x is 1 over the absolute value of x times the square root of x squared minus 1. Okay, so that's the formula. We're going to be using the chain rule here, so we're going to be using u for x to the third, and then we'll differentiate x to the third afterwards. All right, so let's go ahead and find the derivative. We're going to be using the chain rule first so that we can differentiate this radical function. So f prime of x, focusing on the radical function, that's going to give us, I like to use this shortcut to save time. You have to recall that the derivative ddx of root x, I shouldn't have written it like this. ddx of root x is equal to 1 over 2 root x. Okay? So you can use this to save time. So I could use that here instead of using the power rule, which would take forever. But since we have a complicated problem, we can always use shortcuts. Okay, so let's use this formula. I hope you see how this works, because x to the 1/2, if you use the power rule, you're going to have 1/2 x to the negative 1/2, which is 1 over 2 root x. Okay? All right, so if I apply that there, here I'm going to have 1 over 2 root u. Okay, 2 root u, but u is this entire argument of the radical function, so 2 root x to the third plus x divided by the arcsecant of x to the third. Okay? All right, we're done with the outermost function. Now we're going to shift our attention to the inner function. So to do that, we're going to have to use the quotient rule. Okay? When I'm using the quotient rule, u is going to be x to the third plus x, and v is going to be the arcsecant of x to the third. Okay? So let's go ahead and do it. We're going to do vu prime first. We already know what the quotient rule is. So v is the arcsecant of x to the third. V and then u prime, just simplify the power rule here. You're going to have a 3x squared plus 1. 3x squared plus 1 minus, this is v u prime, and then minus u, which is x to the third plus x. That v prime is going to be, we're going to be using a chain rule here. So first of all, we have 1 over the absolute value of u, which is x to the third, okay, times the square root of x to the third squared, simply x to the sixth. Let's just combine steps to save time, minus 1. Okay, so that's the derivative of the outer function, looking for v prime. And then if we differentiate x to the third, that's simply going to be 3x squared, applying the power rule to x to the third. Okay, so this is vu prime minus uv prime. Don't forget the denominator, that this whole thing divided by v squared. All right, so that's going to be v is going to be the arcsecant of x to the third. That's v, right? So we're going to square that. Okay, so that's the derivative. Let's just put it together. You don't have to simplify too much, but let's just put it together into one nice little fraction. F prime of x is going to be 3x squared plus 1 times the arcsecant of x to the third minus, now the numerators, I can put all the numerators here together, 3x squared times x to the third plus x, that divided by the denominator, which is the absolute value of x to the third times the square root of x to the sixth minus 1, and then this whole thing divided by, since we're multiplying two fractions, 1 times that is just what you had before, and then these two terms in the bottom will be your denominator, so it's going to be times 2 times the square root of x to the third plus x over the arcsecant of x to the third times the arcsecant of x to the third raised to the second power. Okay, so if you gave me this answer, that's fine. You know, this is just trying to put it together. You don't have to simplify that much for these problems. I just want to make sure that you know how to make use of the rules of differentiation. Okay, so this is going to be your final result for question number 3. All right, let's take a look at question number 4. So for problem 4, we have y equals log raised 2 of tan 2x raised to the cosine of 3x plus 1. Okay, Anyway, when you have a situation like this, a function raised to a functional exponent, you're going to have to use logarithmic differentiation, okay? So let's go ahead and use logarithmic differentiation to find y prime. So let's write down what the problem is completely. If y is equal to that, find y prime, okay? So that's a task. So first thing you're going to do, if you want to use logarithmic differentiation, is to take the natural logarithm of both sides of the equation, all right? So you take the natural logarithm of y equals the natural logarithm of log base 2 of tan 2x raised to the cosine 3x plus 1. Alright, so using the properties of logarithm, we know that we can power down this exponent. Power it down. So we are going to have the natural logarithm of y equals cosine 3x plus 1 times the natural logarithm of log base 2 of tan 2x. Okay? Okay, now, as you can clearly see on the right side when we're differentiating, we have to use the product rule. Okay, and we know remember what the product rule is. uv prime is equal to vu prime plus uv prime. Alright, so that's what we're going to be doing here. In this case, we can see what u is. U is cosine 3x plus 1, and v is the natural logarithm of log base 2 of tan 2x. Okay, so let's go ahead and differentiate both sides. On the left side, differentiating implicitly, derivative of ln x is 1 over y times y prime. Okay, because we're differentiating with respect to x and the variables don't match, so we have to add this y prime component. Alright, so now we're going to use the product rule. V is the natural logarithm of log base 2 of tan 2x. So that's v, and then u prime is the derivative of cosine. The derivative of cosine is negative sine, right? So let's put the negative up front here. Negative sine 3x plus 1. So that's sine, we're differentiating cosine u. Now if we differentiate the innermost function, this linear function will be times 3. Alright, so this is vu prime plus u, which is cosine 3x plus 1. Now if we differentiate this, the natural logarithm of that is going to be 1 over, if you're looking for v prime, the derivative of of v is going to be 1 over u, okay, times the derivative of that. So it's going to be 1 over u, so I can just put, since it's 1 over u, let's put it right here, times 1 over, the denominator is going to be log base 2 of tan 2x. Alright? Because we know that the derivative of ln x is 1 over x. Okay? So now let's differentiate. We're done with the ln. Now let's shift our attention to log base 2. Remember what the derivative of let's write it down so we don't forget. So you have log, so it's a weird one to remember. Log base b of x prime is 1 over 1 over x times the natural logarithm of b. Alright, so that's what we're going to have here. So it's going to be 1 over x is tan 2x. Okay, so it's going to be 1 over tan 2x times the natural logarithm of the base. What is the base? 2. Okay, 1 over x is 1 over tan 2x times the natural logarithm of the base. Alright, and then lastly, we're going to look for the derivative of tan 2x. Okay, so what's the derivative of tan? Remember what the derivative of tan is. Let's recall. Tan x prime is secant square x. Okay, that's the derivative of tan. So if we differentiate tan 2x, we're going to have to use the chain rule again. Let me shift it to the left a little bit. So u is 2x here, so derivative of tan u is going to be secant square u. So we're going to have secant square 2x. Now to differentiate 2x is going to be just 2. Okay, so there you have it. Now what we're going to do is we have to multiply both sides by y, right? So we'll multiply both sides by y. We're going to replace y with its value, which is this logarithmic value right here. Okay, so we're going to replace that and then times this entire expression. That will be what our final result will be. So if I multiply both sides by y and substitute the actual value of y, so what I'm doing now is I'm multiplying this side by y, multiply this side by y, and multiply this entire equation by y. Okay, so multiplying and replacing with the original value. The original value of y is log base 2 of tan 2x. That entire thing raised to the cosine 3x plus 1. Okay, that was what y was originally. Okay, right here. And then that times this entire expression right here. Okay, so times, let's see how we can make this look better. We can just bring the 3 to the front. So it's going to be minus 3 times the natural logarithm of log base 2 of tan 2x. Log base 2 of tan 2x multiplied by sine 3x plus 1. And then we can compress this easily. Compress it, make it look a little bit nicer. So if I compress the numerator, just multiply the numerators across. I'm going to have 2 cosine 3x plus 1 secant square 2x. And then that divided by the denominator, which is log base 2 of tan 2x times tan 2x multiplied by the natural logarithm of 2. Alright, so there goes your final answer for question number 4. Good day, students. In this clip, we're going to be going over an example on how to use implicit differentiation to find the equations of a normal and tangent line to the curve of a rotated ellipse. Okay, so let's go ahead and write down the instruction for this example. All right, so the task is we are to find the equations. Find equations of the tangent and normal lines to the curve of the graph, or the curve of the equation given by x squared plus 2xy plus 3y squared equals 9. We want to find the equation of the tangent and normal lines to this curve at the point 1, -2. All right, so that's our task. All right, so before we start, let's go over the formulas that we're going to be using in this to do this problem. So the formula that you need to know is basically a basic algebra 1 formula. Okay, the equation of a line. We're going to be combining that with calculus. So for equation of tangent line, that's going to be given by y minus y1 equals x minus x1, where m is equal to dy dx at the points dy dx at x1, y1. Alright, so what this formula is telling you to do is, in order to write down the equation of the tangent line, you need to find the slope at that point x1, y1 by implicitly differentiating whatever function you have, and then put it into the point slope form of the equation of a line. Alright, so that's for a tangent line. And then for the equation of a normal line, it's gonna be y minus y1 equals mx minus x1, where the slope here, m, is going to be equal to the negative reciprocal of m of the tangent. Okay, so this basically tells you that to get the equation of the tangent normal line, you take the slope of the tangent line and you do the negative reciprocal or the inverse, and then plug it into the point slope equation. All right, and then that's what you're going to do. All right, so let's go ahead and apply that. Let's see, formulas to this problem. We have x squared plus 2xy plus 3y squared equals 9. All right, so first thing we're going to do is find dy dx and then evaluate it at the fixed point 1 comma negative 2. Okay, so we're going to differentiate implicitly here. Applying the power rule, here we have 2x, dx drops off, and then plus. Now let's differentiate this. I'm going to factor out a 2, and we're going to use the product rule. Okay, so remember what the product rule is. Let's put that on the side here. uv prime is equal to v u prime plus u v prime. All right, so in this case, x is our u and y is our v. All right, so let's go ahead and differentiate it. V is y, u prime is going to be times 1 dx plus u, which is x, times v prime, which is times derivative of y is just 1, and then dy dx. All right, that plus, now let's differentiate the last term. Using the power rule, we have 6y dy dx. Okay, that equals to the derivative of 9, which is simply 0. Okay, now let's simplify this and isolate dy dx. So we're going to have 2x plus 2y plus 2x 2x dy dx plus 6y dy dx equals 0. Okay, so to get dy dx, we have to isolate the terms of dy dx on one side, factor out dy dx, and then get dy dx isolated. All right, so these two terms here do not have dy dx attached to them, so I'm going to subtract them from both sides, and that's going to yield 2. And then how about we just factor out dy dx in the process? All right, so if I factor out dy dx from here, I'm going to have 2x plus 6y dy dx equals negative 2x minus 2y. All right, and then to get dy dx isolated, I'm going to divide both sides by 2x plus 6y, and then divide this side by 2x plus 6y. All right, so this divides out, and then we're going to have dy dx, the y dx equals, if you notice, I can divide the numerator and the denominator by 3, I mean by 2. 2 is a common factor, so I'm going to have negative x minus y over x plus 3y. Okay, that's as a result of dividing it by the GCF, 3 top and bottom. Okay, all right, so this is the slope at any point, xy. Now, we're going to go ahead and find the slope of the tangent line. M of tangent is simply going to be dy dx evaluated at the point 1 comma negative 2. All right, so M of tangent is going to be negative parenthesis 1 minus negative 2 over 1 plus 3 times negative 2. So how did we get this? By plugging x and y into this dy dx equation, which helps you calculate the slope at any point. All right, so we'll simplify that. We're going to have negative 1 plus 2 over 1 minus 6. This is going to give us 1 negative 1 over 5. So that's the slope of the tangent line. Okay, m of tangent is 1 over 5, so m of normal Slope of the normal is basically the negative reciprocal of the slope of the tangent, which is going to be the negative reciprocal of negative 1 over 5. So we can just reciprocate this and invert the sign, which is going to give us 5 as the slope of the normal line. Okay? Alright, so let's write down our solutions. So equation of tangent line in point slope form can be written as y minus y1, which is negative 2. So y plus 2 is equal to the slope m, negative 1 over 5 times x minus x1. Okay? x1 is 1, so x minus 1. Alright, this is a point slope form. We can also write this in slope intercept form, getting y by itself. We get y by itself. Distribute 1/5 here is going to be negative 1 over 5x. And then this will be plus 1 over 5 minus, plus 1 over 5 minus 2. 2 can be written as 10 over 5. So if we have plus 1 over 5 minus 10 over 5, you're going to have negative 9 over 5. Negative 9 over 5. Alright? So there goes the equation of your tangent line. How about the normal? Equation of the normal line. Remember, your normal line is perpendicular to your tangent, right? That's why we take the negative reciprocal of the slope of the tangent line to get the slope of the normal line. Alright? So the equation of your normal line, same process, the only difference here will be your slope. So y minus y1, which is y minus minus 2, which is y plus 2, equals m. The negative reciprocal, found out that here, of this is 5 times x minus 1. This is a point slope form. We want to write it in slope intercept form. Just get y equals, distribute the 5 to x, 5x. Distribute 5 here, negative 5 minus 2, minus 7. Okay? So these are our two equations. The equation of the tangent line and the equation of the normal line. Alright? Okay, so let me give you a graphical representation of the situation so you can really see the connection between the geometry of what we're doing and also the algebraic component. Alright, so let's say we have a coordinate system like this. This is what the graph looks like. This is a graph the curve that's under consideration. We see it's an ellipse that's been rotated. Now if I graph the point, negative 1, negative 2, you can see that point provided right there. Alright, now what does the equation of the tangent line look like? We said it was y equals negative 1 over 5 x minus 1 plus 2, or negative 1 over 5 minus 9 over 5. If I generate the curve, you see how it looks like. This is a tangent line. It intersects the curve at exactly one point, tangential at the point 1, negative 2. And then the normal line, do you know what it's going to look like? The normal line is going to be perpendicular to this line right here. Let's go ahead and sketch it. So there goes your normal line. Alright? Alright, so I just captured the graph that I just sketched. Alright, so let's go ahead and label the equations. So this one right here is this is your tangent line, okay? Tangent line. And the equation is y plus 2 equals negative 1/5 x minus 1. Alright? And then this is the actual curve. The curve that has the equation x squared plus 2xy plus 3y squared equals 9. And then last but not the least, this is your normal line. Normal line to the curve at that point. Alright, so let's spell that correctly. Normal line. Normal line. And the equation we found to be y plus 2 equals 5 times x minus 1. So that's the equation in point slope form. So remember, your normal line is perpendicular to your tangent line. So the angle of separation between these two lines is 90 degrees. All right, so this is basically a graphical representation that shows that our answer is in fact correct. Okay, I generate. Okay, students, in this clip we're going to be going over two examples on how to find the derivative of the absolute value and piecewise defined functions. Okay, so let's take a look at question the first problem. So in this one we are to find y prime for y equals the absolute value of sine x squared. All right, so we're gonna do this using two methods. We're gonna find y prime for y equals sine absolute value of sine x squared using exponents. And then we'll verify our results. Then verify your results using the formula the formula for the derivative of absolute value functions. Using the formula, the absolute value of u prime is equal to u times u prime over the absolute value of u. Okay, so we're going to first of all find the derivative of this function using exponents. Then we're going to use this formula to verify that our result is correct. Okay, so method one is the method of exponents. Using exponents. All right, so how do we approach this problem? The idea of finding the derivative using exponents? Well, that involves rewriting this absolute value function using exponents. Okay, so absolute value of sine x squared can be written as the square root of sine square of x squared. Okay, you have to remember remember that if you take the square root of x squared, for instance, this is equal to absolute value of x. So the square root of a square is another way of writing the absolute value of the argument or the radicand. Okay, so that's exactly what I did here. I took the square root of the square of this term inside the absolute value bars, and that's how I expressed it like this. All right. So this is what we're going to be finding the derivative of this function right here. Okay, so let's write it again. So y is equal to the square root of sine square x squared. Now, how many functions do we have in this function right here, this composite function? We have the radical function 1, we have the square function, the power function 2, we have the trig function 3, and then we have the quadratic function 4. So we have 4 functions. That means we're going to be using the chain rule 3 times, since we don't need the chain rule for the innermost function x squared. All right, so let's go over the formulas that we're going to be using to find the derivative of this function. So formulas, we're going to be starting from the outside all the way in. Okay, so the outermost function is a radical function, so we're going to be looking for dx of the square root of u. Root u because the argument, the radicand of the square root function is a function itself. Okay, so the derivative, there's a shortcut you can use. This is 1 over 2 root u. This is the shortcut of using the power rule. If you use the power rule and simplify, this is what you end up with. Okay, so you have 1 over 2 root u du dx. All right, and then the next function is a square function. Remember, sine is being raised to the second power. So dx of u squared, since a function is what's being squared, not a variable. If we apply the power rule here, this is going to be 2u du dx. All right, and then next we have the trig function sine x. So we're going to find ddx of sine. Now, since sine is also a composite function, sine is being composed with x squared, we're going to have sine u. In this case, the derivative of sine is cosine. So it's going to be cosine u du dx. All right, so there goes the application of the chain rule 3 times, and then the innermost function x squared, which is going to find ddx of x squared. We don't need the chain rule here, which is equal to 2x. Okay, all right, so the product of all these using the appropriate u substitution will give us what the derivative of the function is. All right, so let's go ahead and find y prime. So y prime is going to be 1 over 2 root u, so it's going to be 1 over 2 root u. Root u is sine square x squared for the radical function. So 1 over 2 root sine square x squared. So that's the first one. Now shift your attention to the square function. So the derivative of the square function is 2u, where u is sine x squared. So it's going to be 2 times sine x squared. Okay? And then next, the derivative of cosine u is cosine u, where u is x squared. So if we differentiate that, we're going to have cosine x squared. And then last but not the least, the derivative of x squared, which is 2x, so times 2x. Okay? Alright, so that basically is the derivative. Let's rewrite it in a nicer form. So y prime is equal to, let's write the constants first. So we have, let's see. Yeah, these two 2's divide out. So this 2 and this 2 divide out. And I can put the 2x first, so I can write this as 2x sine x squared cosine x squared, and then this entire expression divided by, now the square root of the square root of the square of sine is the same thing as the absolute value of sine, right? Where the argument of the sine is x squared. Remember what we did earlier. So square root of the square is absolute value. Okay, so you can go in this direction or you can go back. So this is the answer using exponents. Now we're going to do the same procedure using the formula and then see if we have a match. If we have a match, we're confident that our answer is in fact correct. Alright, so for method 2, we're going to be using the formula. So let's go ahead and write that down. So this is verification. Verification using formula. Okay, all right, and then the formula that we're talking about here is is the derivative of the absolute value of u is equal to u times u prime over the absolute value of u. All right, so that's the formula. In this case, we have y is equal to absolute value of sine x squared. So we can clearly see that what we're taking the absolute value of is sine x squared. So u is equal to sine x squared. So u is equal to sine x squared, then that follows that u prime, we're going to have to use a chain rule here since we have a composite function, is going to be sine x squared. I'm sorry, if we differentiate the parent, the derivative of sine is cosine, so it's going to be cosine x squared times the derivative of the input x squared, which is 2x. Alright, so that's what u prime is. Alright, now we're just going to put u and u prime into this formula right here and see if we have a match, okay? So y prime is going to be u. U is sine x squared times u prime, which is cosine x squared times 2x, divided by the absolute value of u. And we know what u is sine x squared, so absolute value is sine x squared. Okay, so we can rewrite this as 2x sine x squared cosine x squared divided by the absolute value of sine x squared. Alright, so divided by the absolute value of sine x squared. So the question is this a match? Is this the same thing as what we had before? Alright, let me just box it and then we can do a comparison. Let's do a real quick comparison right here. If I scroll it up, you see that they have a match. Okay, they're identical, so we're confident that our answer is in fact correct. Alright, so there you have it. Alright, let's take a look at the next question. So in this case, we are to find the 5-part problem. Part A, the limit as x approaches 1 from the right of f prime of x. B, to find the limit as x approaches 1 from the left of f prime of x. C, you to find the limit as h approaches 0 from the right of f of 1 plus h minus f of 1 over h. And then for d, you're going to find the limit as h approaches 0 from the left of f of 1 plus h minus f of 1 divided by h. And then part e is f of x differentiable at x equals 1. Is it differentiable at x equals 1? Why or why not? Okay, so you basically use your answers from these four previous parts to arrive at a conclusion, which basically indicates whether the function is differentiable or not at x equals 1. And all of this you're going to do for the function for the piecewise defined function f of x equals x minus 1 square for x is less than 1, and then 3 times the natural logarithm of x for x greater than or equal to 1. Okay, so this is a function that we're dealing with here. All right, so in order for us to answer part A and B, we need the derivative of this function right here, and then we can then take the limit as x approaches 1 from the left and right. Okay, so let's take the upper function. For x is less than 1, we have f of x equals x minus 1 square. So what's the derivative of this one right here? So f prime of x, we're going to use a chain rule here, is 2 times x minus 1 times 1, okay, which is equal to 2x minus 2. So that's the derivative of the function for x is less than 1, okay? And then for x greater than 1, we have the function f of x equals 3 times the natural logarithm of x. So when we differentiate that, f prime of x, you're going to have 3, the derivative of ln x is 1 over x, okay? So you have 3 over x, okay? So if this is the function, then the derivative function, that implies that the derivative function f prime of x is going to be this one, 2x minus 2, 2x minus 2 for x is less than 1, and then this one, 3 over x for x is greater than or equal to 1. Okay, so those are the two piecewise functions that we have here. Alright, now that we have the functions, we can now proceed to finding the limit from the left and the right of the derivative. So let's see what we have here for the a part. We're to find the limit as x approaches 1 from the right of f prime of x. So if we're approaching 1 from the right, this will be the function that we're looking at right here. So we're going to be looking at the situation where we plug in 1 into this function at the bottom. So it's going to be 3 over 1. Alright, so 3 over 1 is equal to 3. Okay, so that's the value that the derivative is approaching from the right. Okay, and then the b part, we're to find the limit as x approaches 1 from the left of the function of f prime of x. So the derivative function, if you're approaching from the left, this is a function that's active, so we're going to plug in 1 into the x here. So we're going to have 2 times 1 minus 2, which is 0. Okay? So this is the value that the derivative is approaching from the left. Okay, so now let's look at the limit definition of a derivative from two directions. So for the first one, we have the limit as h approaches 0 from the right of f of 1 plus h minus f of 1 over h. Now what is this? What on earth is this? This is the limit definition, directional limit definition of a derivative. We are approaching the derivative from the derivative from the right. So this is known as the right-handed derivative. Okay. So the right-handed derivative is the same thing as f prime of 1 from the right. Okay? And that's the same thing as part A. This is the same thing as the limit as x approaches 1 from the right of the function. So guess what? We already have our answer, the same answer as A, so the answer is 3. That's your right-handed derivative. Okay? And in part D, you already know what the answer is. The limit as h approaches 0 from the left of f of 1 plus h minus f of 1 over h. This is the left-handed derivative approaching as you're approaching the value of x, which is 1. Okay, so that's f prime, same thing as f prime of 1 from the left, which is the same thing as the part B, as you might have expected. The limit as x approaches 1 from the left of, sorry, it's supposed to be a prime here, of f prime of x. Okay, what value is the left-hand derivative approaching? So we already know what the answer is. The answer is 0. Okay, so part E, is the function differentiable at x equals 1? The answer is absolutely not. What we found out that is that the left and the right hand derivatives are different, so the function is not differentiable at x equals 1. Okay, so the function, write down the answer first and then the reason, is not differentiable at x equals 1 because the left and right hand derivatives are different. The left and right hand derivatives are different. Derivatives are different. So you have to remember that the derivative is a limit. Okay? That's why it doesn't exist sometimes, because sometimes the derivative from two directions to a point are different. Okay? Good day, students. In this clip, we're going to go over some examples to review differentiation. We're going to be looking at the differentiation using limits, differentiation of graphs, and then the average value, and also using the differentiation rules to find derivatives at certain points. All right. So let's take a look at question number 1. So for question 1, we are to express the limit as a derivative. Express the limit as a derivative and evaluate it. All right. Okay, so the limit expression under consideration for number 1 is the limit as h approaches 0 of 2 raised to the 2 times negative 1 plus h minus 1/4. And this entire thing divided by h. Okay? Now, what is this in derivative form? Alright, first of all, let's go over the formula for how to express the derivative as a limit. So formula. So the derivative at any value x, f prime of x, expressed using limits, is the limit as h approaches 0 of f of x plus h minus f of x over h. Okay? This is the derivative at any point x. Well, this limit doesn't have any x in it because it is a derivative evaluated at a point. So what is the derivative evaluated at a point using limits? F prime of a. F prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. Okay? So basically, if you evaluate the limit at a point, instead of x, you have a. So if we take a look at this expression right here, what is the value of x? Or where is x positioned? Well, guess what? Whatever you're adding to h, that should be a telltale sign as to what? x is. Okay, in this case, this is x. Okay, x is having a value of -1, so we're evaluating the derivative of a function, of some function at x equals -1. Alright? So with this information, we can easily tell that f of x plus h is going to be this function, but instead of -1, I'm going to put h. I'm going to put x, okay? So it's going to be 2 raised to the 2 times x plus h. Alright, so this is the function that we're dealing with. Alright, so this is f of x plus h, then what must f of x be? Well, you just simply replace x plus h with x, so f of x is going to be 2 raised to the 2x. So this limits in derivative form can be written as we're to find f prime of -1 where the function f of x is equal to 2 raised to the 2x. Okay, so this is our first answer, evaluating the derivative of the function 2 to the 2x at -1. The problem also asks us to evaluate the limits, the derivative. So let's find the derivative of this function at x equals -1. So to do this, first thing we'll do is differentiate the function, and then we'll plug in -1 into the derivative, alright? So the function f of x is 2 raised to the 2x. So the formulas that we're going to use are as follows. So formulas, we have two functions here. We have the exponential function composed with the linear function. Alright, so we're going to have to use a chain rule once to go from the exponential function to the linear function. Alright, so let's start with the outermost function, d dx of 2 raised to the u. We're using u for the power because the power of this exponential function is a function, so that indicates the importance or the necessity of using the chain rule. Alright, so the derivative of 2 to the u using the rules is 2 to the u ln of the base, which is 2, du dx. Okay? Alright, now then the innermost function, which is a linear function 2x, d dx of 2x is equal to 2. You don't need the chain rule here because this is not a composite function. Okay, so putting these two together will tell us what the derivative of this function is. So we can see that f prime of x is going to be 2 to the u ln 2. So it's u in this case is 2x, so it's going to be 2 raised to the 2x ln 2. du dx is the derivative of 2x, and we already found out what that is, which is 2. So times 2. Okay? Alright, so we're asked to find the derivative at -1. So we're going to find f prime of -1. F prime of -1 is equal to 2 raised to the 2 times -1 times the natural logarithm of 2 times 2. Alright, so let's simplify this. This becomes 2 ln 2 over 2 raised to the -2 is 2 squared. Okay, so that equals, using the properties of exponents, we're going to have 2 times the natural logarithm of 2 over 4. Alright, 2 goes here 1, 2 goes here 2. Your final answer is a natural logarithm of 2 over 2. So that's the derivative of the function 2 to the 2x at x equals -1. Alright, let's shift our attention to question number 2. Question 2. Question 2 is as follows. It's going to be a function example where we're going to make use of the product and quotient rules. Okay, so for number 2, suppose f and g are differentiable at x equals 2, and f of 2 is equal to 3, f prime of 2 is equal to 5, g of 2 is equal to -1 and g prime of 2 is equal to 3. So the task is to find A, or to find d dx of 4fg, and B, we're to find d dx of 3g over f. Okay, we have to find this one at x equals 2. Both of them, we need to find both of them at x equals 2. Okay. All right, let's do the A part. So the A part, we're going to find the derivative d dx of 4 times fg. Using a constant multiple rule, I can factor out 4 from the derivative, so we had to have 4 times d dx of f times g. Okay? Alright, so the formula we're going to be using here is the formula that involves the product of two functions. So the formula is the product rule. Alright, so formula uv prime is equal to v u prime plus uv prime. Okay, in this case, f is our u and g is our v. Alright, so let's apply the product rule here. If we do that, the derivative is going to be equal to 4 times times v, which is g u prime f prime, plus u, which is f v prime, which is g prime. Alright, so we're evaluating the derivative at x equals 2. So if we're evaluating it at x equals 2, we're going to have 4 times, it's going to be 4 times g of 2 times f prime of 2 plus f of 2 times g prime of 2. Okay? Now all we just simply do is plug in the values of the functions and their derivatives into this expression, evaluate it, and that'll be our final answer. Alright, so we're going to have 4 times g of 2 is -1 times f prime of 2 is 5 plus f of 2 is 3 times g prime of 2 is 3. Alright, so we'll work that out. We're going to have 4 times -5 plus 9, and our final answer is going to be equal to 16. Alright, so there you have it. Now let's do the B part. Let's partition our workspace so we don't get mixed up. For the B part, we're looking for the derivative d dx of 3g over f. In this case, we can use a constant multiple rule and factor out 3, so 3 times the derivative of g over f. Alright, so what formula are we going to use here? We're going to make use of the quotient rule. Okay, so remember what your quotient rule is. U over v prime is equal to v u prime minus uv prime divided by v squared. Okay, in this case, g is your u, and that's u, and f is our v. Okay, so if we apply the quotient rule to this situation, the derivative is going to be 3 times vu prime is going to be fg prime minus uv prime is going to be gf prime over f squared. Okay, so if we evaluate this derivative at a point, namely at x equals 2, we're going to have 3 times f of 2 times g prime of 2 minus g of 2 times f prime of 2. This entire thing divided by v squared, and we know what v is f, so it's going to be divided by f of 2 squared. Okay? Alright, now we're going to use the chart above to find the values of each function and their derivatives at x equals 2. So if we do that, we're gonna have what are we gonna have? We're gonna have 3 on the outside times 3 times 3 minus -1 times 5. All this divided by 3 squared. So this is going to be equal to 3 times 9 plus 5 over 9. Okay? So notice 3 goes into 9, right? So we can divide that out. We have 3 goes here 1, 3 goes here 3 times. Alright, so we have 9 plus 5, which is 14. 14 over 3. That's our final answer. Okay? So that's that. Alright, let's take a look at question number 3. So for problem 3, the instructions are as follows. It says for the given velocity curve, draw, or basically sketch, draw the related acceleration curve on the same axis. Okay? Alright. So there are 2 ways you can do this. You can think about the slope of a tangent line at different points and then you graph the slope, which is pretty complicated and time consuming. Or alternatively, you can try and think about the function that generates these graphs, differentiate those functions, and then sketch the graph of the derivatives. Okay? So that's the approach I'm going to use. When we take a look at the function here, on the left side right here, this piece looks like a cosine function. Okay? A cosine function with a period of 2 pi, and it has a period of 4 and an amplitude of 2. Okay, so let's just call this is like a cosine function. So v of t is equal to cosine t. This is not being 100% precise. I'm just going to act as though this is your standard cosine function. All right, so on this interval to the left, this is an equation that models the behavior of the curve. And on the right side, it kind of looks like a quadratic function, right? So on the right side, let's say this is your velocity function. V of t is equal to t squared. Is a quadratic function that has been shifted 2 units down, so t squared minus 2. Okay? So in order to find what the acceleration function looks like here, let me change my colors real quick. So let's call the velocity function on this side, on the right side, v of t equals t squared minus 2. So on the left side, to find the acceleration function, remember your SVAJ continuum. If you're going from velocity to acceleration, you just differentiate once, okay? So your acceleration function is going to be the derivative of cosine, which is negative sine t, okay? And then for this interval from 0 to infinity, your acceleration function is going to be 2t. Now, what does a negative sine function look like? We know that sine starts from the origin, and then it goes up, down to the center, and then down, and then back to the center. If you're doing the negative, you're going to do the reverse. So instead of going up, it goes down to the right and up to the left. So it's going to go from here, it's going to max out there, and then come back to the center right there. All right? So it's just a portion of your sine curve. So we can connect the dots like that as best as we can. And then that's a sketch of the derivative of this portion. We can see why that's the case. Here the derivative is 0, and then here the derivative is positive 1, and then here the derivative is 0. You can see how that behavior is replicated by the component of the negative sine t curve from 1 to negative 2. Alright, and then here this is like a quadratic function shifted 2 units down. The acceleration function is given by the line 2t. So the slope-intercept the y-intercept is 0 and the slope is 2. So let's go ahead and graph that here. So let me make it the blue line. So we're graphing it from here, from the center, because the y-intercept is 0. We're going to rise 2 and run 1. So that's what your line will basically look like. Alright? So this function we have just drawn is your acceleration curve, given this red velocity curve right here, okay? So the graph in blue is a of t, and the graph that's in red is your velocity function v of t. Alright, so there you have it. Alright, let's take a look at question number 4. So for problem 4, instructions are as follows. The following chart, this chart provided down here, following chart gives the position s of t of a moving body, in seconds. Okay, so we have this chart right here. So the task is to we're to find the average velocity, from 3 to 17. Alright, from 3 to 17. The B part, we have to approximate the instantaneous velocity, velocity at t equals 8. And then part C, we're to approximate the instantaneous acceleration at t equals 8. Okay? Alright, let's start from the first part. The A part, we have to find the average velocity. Okay? So before we do that, let's write down the formula for the average velocity and average acceleration. Okay? So formulas. So the average velocity is equal to delta s delta t. So let's say we're looking for the average velocity on an interval AB. Okay, so it's going to be given by the slope of the secant line through those 2 points, a comma s of a and b comma s of b. Okay, so to find the slope, we're going to do s of b, which is like your y2 minus y1, which is s of a, divided by x2, which is b, minus x1, which is a. Alright, so that's your average velocity. And you wanted to find your average acceleration. That will be the slope of the secant line using your velocity coordinates as your points. Okay, so that's going to be delta v, delta t. So let's say we were evaluating it from a to b, for example. It's going to be similar to this, only that we're going to be using the velocity functions to compute our points. Okay, so it's going to be v of b, that will be our y2 minus v of a, that's y1, divided by x2, which is b minus x1, which is a. Alright, so these are the formulas we're going to be using for these problems. Alright, so part A asks us to find the average velocity on the interval 3 to 17. So let's write that down. Average velocity. The average velocity is basically given by, let's use this formula right here, delta s over delta t evaluated from 3 to 17. That's what the problem asks us to find. Okay, so if we do that, we're going to have S. In this case, B is 17, A is 3. Okay, so S of 17 minus S of 3. That divided by 17 minus 3. Okay, divided by 17 minus 3. Alright, so we just use our charts to figure this out. So if we look at our chart, S of 17 is 26, minus S of 3 is 6, 17 minus 3 is 14. If we reduce this, we're going to have 20 over 14. We'll divide top and bottom by 2. We'll have 10 over 7 as our average velocity. It's going to be 10 over 7 feet per second. Okay, so do not forget to include your units in your final answer. So 10 over 7 feet per second. Alright, let's shift our attention to the B part, part B. We are to find the we're going to approximate the instantaneous velocity at t equals 8. Alright, so the instantaneous velocity at t equals 8 can be written by v of 8. So v of 8 is basically, can also be written as s prime of 8, the derivative of the position at 8, because you know the derivative of position is velocity. Okay, so we're going to approximate this. This is going to be approximately delta s over delta t evaluated from 5 to 10. Okay, how do we know that we're going from 5 to 10? Well, if you look at the chart, we're finding the average velocity. We are approximating the instantaneous velocity at 8. So we're going to pick a number before and after 8 so we can have the slope of that secant line to tell us what it is. Alright, so we pick 5 and 10 as the intervals around 8 to calculate the slope of the secant line on the position graph. Okay, alright, so that's how we have 5 to 10. Now let's go ahead and figure that out. This is going to be equal to S of B, which is S of 10, minus S of A, which is 5, divided by B minus A, 10 minus 5, using this formula that we had up here. Okay, so if we use our chart, S of 10 is 16, minus S of 5, which is 9, divided by 10 minus 5, which is 5, and then our final answer is going to be 16 minus 9 is 7 over 5 unit feet per second. All right, so this is your approximate instantaneous velocity at t equals 8. All right, so let's go ahead and box that. Okay, let's shift our attention to the last portion, which asks us to find the to approximate the instantaneous acceleration at t equals 8. Alright, so for part C, we're looking for a of 8. So that is equal to what? Remember, if you differentiate your velocity, you get the acceleration, right? So this is equal to the derivative of the velocity at 8. Alright? So in order to approximate this, we're going to be calculating the slope of a secant line using 2 points on our velocity time chart. Okay, notice we're given here, we're provided with the position time chart, so we have to basically come up with the velocity time chart and then find the slope of a secant line around 8 to approximate our instantaneous acceleration. Alright, so to do that, we're going to be using delta v over delta t on what interval? What interval are we going to be looking here? Well, let's go up. We want to find the instantaneous acceleration. So what we have to do is we're not going to be using the time and position function. We need to use these two values and these two values to create a new chart, our velocity and time chart, and then we can use the slope of the 2 points we created to find our approximate acceleration. Alright, so what I'm going to do is I'm going to extend this interval a little bit. So I need an interval from here and then I need an interval from here. Okay, so how do we find those? All we simply do is we're just going to average. Okay, so if I average these two times, I can have a point here that I can use to calculate the first point of my velocity, and then another point here. Alright, so to find the midpoint here, all we just do is average these two. So this point is basically 5 plus 8 over 2 to get this point right here, which is equal to 5 plus 8 is 13 over 2. So that will be our lower bound of the point, less than 8, to make my velocity time chart. And then for this one, this point right here, we're going to do 8 plus 10, just average these two. Okay, 8 plus 10 over 2, which is 18 over 2, which equals 9. Alright, so that will be my second time in the generation of my velocity time chart. Okay, so to find the approximate acceleration, we're going to be evaluating delta v over delta t from the lower interval we created, which is 8 plus 5 over 2. I'm going to write it the way I ordered it up there, which is 5 plus 8, I think I did. So the lower interval, lower boundary is 5 plus 8 over 2. That's going to be our A, comma, our B is going to be the average of the two upper values, which is 8 plus 10 over 2. Alright, so this is equal to delta V over delta T from, like we did upstairs there, from 13 over 2 all the way to 9. Alright, so now using our formula for average acceleration that we have here, we're going to be calculating V of B, which is 9, minus V of A, which is 13 over 2, and then that divided by B, which is 9, minus A, 13 over 2. Okay? Alright, so now we have a new problem. We have to now find the instantaneous velocity at t equals 9, and also the instantaneous velocity at t equals 13 over 2. Well, since we don't have these, we have to approximate. We're going to be using the approximate values here. Okay, so V of 9 is going to be, V of 9 is the instantaneous velocity at t equals 9. And that is equal to, s prime of 9. Okay, so we have to approximate here. So to approximate here, we're going to be using delta s over delta t evaluated on an interval around 9. Okay, so what's the interval around 9? Let's scroll back up. The interval around 9 is 8 and 10. Okay, so we're going to be going from 8 to 10 to calculate the average velocity. Okay, so we're going to be going from 8 to 10. Okay, alright, so using the formula we went over upstairs, we have s of b, which is s of 10, minus s of a, which is 8, divided by b minus a, which is 10 minus 8. So that's going to be s of is going to be 16 minus 12 using the chart over 10 minus 8, which is 2. So this is simplified. This we have 4 over 2, and it reduces to 2 feet per second. So this is your average acceleration, average velocity at t equals 9. Okay, it's an approximation. All right, and then we also need v of 13 over 2. Instantaneous velocity of 13 over 2 is the same thing as the derivative of the position at 13 over 2. We don't have the function, so we have to use an approximation here. Okay, so we're going to be approximating delta s over delta t evaluated on what interval is the question. So let's go back to the chart. We're working around 13 over 2, which is this boundary right here. So we're going to be going from 5 to 8. Okay, to calculate the slope of that secant line from to this point. So we're going to have the interval will go from 5 all the way to 8. All right, let's try that again, 5 to 8. Okay, so using the formula we went over upstairs, we're going to be computing s of 8 minus s of 5 divided by 8 minus 5. Okay? So this is going to become 12. S of 8 is 12 minus S of 5, 9. Divided by 8 minus 5 is 3. Okay, let's work this out. 12 minus 9 is 3. 3 over 3 is 1. So 1 feet per second. Alright? Alright, now we have all the information that we need to calculate our to approximate our instantaneous acceleration. So let's rewrite down what we had upstairs. So A of 8 is approximately V of 9 minus V of 13 over 2 divided by, let's do that again, divided 13 over 2 divided by, we had 9 over 13 over 2, right? We can write 9 as a fraction and find the LCD, so put 9 over 2 and times it top and bottom by 2, so times it by 2 and times it by 2. So that's going to yield, what's that going to yield? It's going to give us 18 over 2 minus 13 over 2. Okay? So using the results we got, V of 9 is 2 minus V of 13 over 2 is 1 divided by 18 over 2 minus 13 over 2 is 5 over 2. Alright, so in the numerator we have 1 times the reciprocal of the denominator times 2 over 5. If you multiply across, you're going to have 2 over 5. And the unit of acceleration is feet per second square. Okay, so that basically is your approximate instantaneous acceleration at t equals 8 seconds. Alright, so there you have it. But thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking here. And please post a comment to let me know what you think about this clip. And if you liked it, I'll appreciate it if you give me a thumbs up. And feel free to share with your friends. More clips can be found on microsoft.com/calculus.